students. So today I will be talking about something called SAC 305. This is basically a lead-free solder joint. Comprising of silver, Ag, tin, Sn, and copper. Cu. So that's how the name is SAC. S for Sn, A for Ag, and C for Cu. Now, why this is important? Because first of all, this is a lead-free solder joint, which is in very much research nowadays, which is being replaced, which is replacing the lead full solder joints, and this lead being a hazardous substance, as told by ROHS directive, restriction of hazardous substance directive, and WEEE directive. It stands for waste electrical and electronic equipments directive. So we need to find an alternative for any solder which consists of lead. So very much researched substance, or very much substance which is being used nowadays, is this SA305. Its main use is in electronic packaging. Okay, so electronic packaging industry, where two metals needs to be joined, so this solder joint is being used. Now what is the concentration of the different elements in the solder joint? The silver is the main majority of the portion of is silver. It's 96.5%. Sorry, tin is 96.5% on this one. Tin is 96.5%, so the major contribution comes from the tin. Silver is 3%, and copper is 0.5%. Now, what do we need to do? We need to make this solder joint as efficient as possible. Now, what are the limitations that we face while we are using this solder joint? Just an example. Now, how the solder joint is made, for let us first see that. So you have a copper substrate, you have another copper substrate. In between, if you would like to join this copper substrate, you use here this SSC 305. This is how it is being done. Now, whenever we are making such electronic packaging, this electronic packaging will undergo mechanical stress in use. So it needs to be mechanically stable. It will go temperature changes, and it will also go corrosive changes. So it needs to pass all these three tests to become a stable solder joint. Now, what has been observed that the reason why stability gets hampered are because, so let us call the limitations. Limitations include formation of something called an IMC. IMC stands for intermetallic compounds. Now, as we are joining these substances, a lot of chemical reaction will take place in between this solar joint and at the interfaces. So these chemical reactions will cause something called inhomogeneous distribution of intermetallic compounds, and there is formation of scallops, that is inhomogeneous distribution of the different phases formed. Now what are the different phases which are possible at the interfaces? The different phases possible are, first of all, since the mostly it consists of the tin, so beta tin phase is possible. Then you can have a Cu6 SN5 phase, whereas you can also have a Cu3 SN phase. Now these two phases are the one that we are mainly concerned of. We don't want an inhomogeneous distribution of these phases. What we want is a homogeneous distribution. So the lower the number of these intermetallic compounds, the better the performance of these materials. Now, to increase its performance, what is done is, apart from having a solar joint in between, so this is your SSC, an extra layer of tin is introduced. So it's copper, then a thin film of tin, then the solar joint, then again the thin film of tin, and then again the solar joint. So these are called layered solar joints. Layered SAC 305, and one which has no tin layer, they are called non-layered. So the main comparison that we will study today is between this layered solder joint and non-layered solder joints. So what are the advantages that we obtain by putting an extra tin layer, and that we will try to understand. Now firstly, we will start with mechanical testing. And that will be performed, that was performed by something called Nano Indentation. Now what the Nano Indentation does, some basic, I think you already have some basic knowledge. So with a very sharp tip, it penetrates the material and you get a corresponding load depth plot. So this is a P corresponding to load, and this is height. Okay, this is in, basically it's in millinewtons, and this height is in nanometers. And it follows depth sensing indentation. And the technique which is used is called CSM. It stands for continuous stiffness mode. So what this continuous stiffness mode means? It means that as the load is increased corresponding to the depth, so for each particular interval we are unloading the plot. So it is not a smooth curve like this, it is basically unloading. This is how it moves, and for each particular step from the unloading portion we take the slope and we find the stiffness of the material, and this stiffness is basically used in finding the elastic modulus, and the projected area is used in finding the hardness of the material. So that's how we get an depth sensing elastic modulus and hardness. Now, there is another term that is as important to hardness and modulus, that is called fracture toughness. So we are mainly concerned with that for the case of SSC. So it has been observed that if we do the load depth curve of an layered SSC and a non-layered SSC, so the layered SSC is like this, whereas the non-layered SSC is like this. So there is a slight difference. So put it like this is the layered one. This is the layered one. Okay, I was right in the previous case. This is the layered one. That means it consists of this extra thin layer, where this is the non-layered one. So the difference that you can see between the two plots is that there are much more discontinuities or much more steps observed in the non-layered one, and these steps correspond to localized fracture that has taken place while the indent is being penetrated through the sample, and comparatively the localized fracture is much less in case of a layered SSC. That makes the layered one more stable compared to the non-layered one. That's the first thing. Secondly, there is another parameter. So when we did the cyclic voltammetry test, we found that the area with respect to the scan rate was higher in case of the layered samples, whereas much lower in the case of non-layered samples. So that makes it having more charge storage capacity, the layered SSC compared to the non-layered SSC. So there is another aspect. Secondly, conduction was found to be higher in case of the layered one compared to the non-layered one, mainly because of parameters called dislocation density. Dislocation density. Now, the dislocation density in case of the layered joints was higher. So, N in the case of layered ones was higher than N in the case of non-layered one, and this dislocation density N is equal to 1 by d square, where d is the crystallite size obtained from Scherer's equation. So from XRD we first find out the d, and then from d we could find out the N value. So it has been found that the crystallite size in case of the layered samples were much less compared to the non-layered samples. This is mainly because of the fact that the extra thin layer that we have introduced between the both sides of the solder joint, that thin layer prevents any sort of major diffusion taking place. So say this is your SSC 305, and you have a tin layer above it, SNSN. Above that you have copper. So what it is causing, this is causing any major diffusion or any major formation of intermetallic scallops. Okay, so this acts as a diffusion barrier. This extra thin layer acts as a diffusion barrier. So that is why the crystallite size is reduced, and which causes an increase in the dislocation density, and which actually causes an increase in the conductivity of the material. Now, the resistivity or the conductivity is also equal to phonons So due to lattice vibration plus defects in the material, it is called Matt-Hyson's rule. So you can see that the higher is the dislocation, that is the defect, the more will be the resistivity, so less will be the conduction. So that is how the layered samples are more conducting compared to the non-layered samples. And this phenomena can be also be understood by something called nonlinear ultrasonic characterization. So we send an ultrasonic wave through the material, and it ultrasonic waves gets reflected from the defects, and by analyzing that we can actually find out the nature of the defect in the material. So without going into the details, the parameter that we are mainly concerned is called parameter beta in nonlinear ultrasonic characterization, and it is equal to 8a2 divided by k square E1 square into x. But E1 and A2 are displacement amplitudes. These are called the displacement amplitudes of the first and second harmonics. So there is a differential equation and there is a harmonic generation. So these are the amplitude of the first and second harmonics. K is the wave vector of the sound wave, of the ultrasonic wave that we are sending, and x is the propagation distance, the distance for which the ultrasonic wave has traveled. Okay. Now this beta, let's put it in different color. So this beta of the layered sample is found to be greater than beta of the non-layered sample, and beta is again related to the dislocation density and the conduction as NL to the power 4 into sigma. Sigma is the applied residual stress, N is the dislocation density, this is the stress which is applied, and L is the dislocation loop length. So here also you can see that beta is proportional to the dislocation density, and that's how a higher dislocation density will cause a higher value of beta. The higher is the value of beta, the better the conduction that takes place.